And now it's time for Anders Holst, who will talk perhaps a little bit about some of the basics of machine learning and also perhaps some of the troubles you can run into when you try to apply it in practice.
Yes,
all right, welcome.
I will try to set the machine learning in some kind of context, what you need to think about around this to make it work. So in these big data times, it's usually you think that if you have this just a huge set of data with the right kind of analysis, you can get out huge value from it. And unfortunately, it's not that simple, because just because you have magnitudes more shit in, you wouldn't suddenly just get value out. So you need to have the right. There's a lot of more things that need to be right. So a better way of looking at it is that it's not really the data that is interesting. It's actually something in the real world you're interested in. So the data is merely an incomplete, noisy, faulty trace of hopefully something you are interested in here. So the best you can do is to use the data to build a model of the aspects of the real world of interest. And then you use the model to make some conclusions. And this is, so it requires you to know something about, do you have the right data, and what is the interesting aspects you need to model. So it's not so much of a black box solution as you might think. And this is where machine learning comes in, because machine learning is one way to build models from data, but you must do it in the right way, kind of. So, machine learning, you use actual data to train a model, which can be used to solve various tasks, as we just heard Danny talk about several of those tasks. But there's a big diversity of tasks and parameters here. For example, there are different kinds of tasks. Classification was it's of course the most common one, but you can also have clustering when you don't know exactly what the different classes are. You want a method to categorize things for you. And anomaly detection is also very popular when you don't know what you're looking for. You just want to find something that is different from what you have. And there are huge amounts of huge areas of application where you can use machine learning. And also there are various kind of input data or different data types. So it seems it might be easy as long as if you only have binary data in, it might be easy, but it's harder when you get us to pictures, as Danny was talking about a lot at least, but other time series of various kinds, natural language and so on. So there is a big diversity of problems and challenges and methods and so on. So I will immediately go on to talk about different machine learning methods. So the easiest kind of machine learning is probably the case-based methods, when you actually you just take all the data you have and put it in a large table, and then you want to find when you get a new sample and you want to classify it, you just find a matching one in the table, or one that is as close as possible to the one you have in the table. And then you say it's the same class. And that's nearest neighbor is a very common method there, for example. So it's very easy to train this method because you just store everything you see. But of course, also in a big data context and in streaming data, your training set will grow and grow and grow and become very large. And in the retrieval phase, when you want to find out what you have learned, it might take longer and longer time than to search through this huge amount of samples to find the right thing. So another category, these are the 5 course categories of different approaches to And so the next large category of machine learning methods builds on logical inference, where you typically try to, instead of storing all your huge amounts of data, you try to find a logical expression that characterizes the data. For example, if x is bigger than 2 and y is less than 3, then it's probably an apple, you see, or something. A simplified example. So find some, based on the features you have, find some simple logical rules to classify it. There are several, several methods there as well. A popular set of methods now is what is called random forests, for example, which in turn consists of a large number of decision trees, which uses this a sequential set of rules. First, check one feature and see is it less or more than some value, and then you go into the second rule, and so on. Okay, and then we come to this area, of course, of artificial neural networks. That's what Danny was focusing on, at least. Where there are also a large number of different architectures, but the deep neural networks are the ones most popular now, I would say. The principles here is very different from the logical inference. Instead of just having strict rules, what yes or no or below and so, you weigh together evidence, just like Danny also showed in his network of, you add up the features weighted in different ways and do that in several layers, kind of. So there has been a kind of conflict from the beginning of AI, some 60 years ago. There has been a kind of conflict between the hard AI people and the soft AI people in what you are doing, because according to the hard AI, well, we are trying to mimic how humans work, and humans think rationally. They think in rules and argue with strict logic and so on. That's what is human, to be human. And whereas the neural network people more say, no, it's not. The difficult things for a computer is things like, recognizing an image, if it's a cat or a car or something, or recognizing what someone says to you. And then it's not so clear-cut anymore. It's more like weighing together evidence and picking the one that seems most likely and so on. So it's much more softer and so on. So there has been a kind of conflict between these ones. And for a long time, actually, they started to converge using the next big category of methods, statistical machine learning methods. So this is also a huge field of very different methods, because it turns out, of course, that both the logical methods and the artificial neural networks and the case-based methods can be cast in statistical terms. So what is common here is that you try to look at your classification problem as making estimating a probability distribution over your classes and picking the class that is most probable given the input you have. So for a long time, I would say that the field converged towards statistical machine learning methods. Everyone started to reformulate their methods as statistical methods, until then recently with this deep learning that is actually when suddenly neural networks took back some of the attention with these deep neural networks. But anyway, things have converged, so that there is a lot of overlap between the different approaches. A final approach I want to mention, sometimes it's not considered its own approach, but I think it should, these heuristic search methods. The most famous is genetic algorithms, where you kind of, but in general here, you have a model and you tweak your parameters of your model so it should fit the data as good as possible. And you can use that in different ways. And sometimes these methods can be used also as training methods for the other machine learning models. So there is a big overlap between all these categories. And of course, you can have hybrids between the different approaches and play within a different way. But I think these are the main approaches for machine learning. And they are very different in their backgrounds and basis and so on. However, that's not all there is to machine learning, selecting method, because I didn't say which method is best, which is the best method. That you can't say, actually. They are good at different things and in different contexts and so on. And there are no clear-cut rules when to use one method over another, though. And maybe, I will now come to this. So you have these machine learning methods, different kinds, and you have to select your method, of course. And once you selected your approach, there is a lot of parameters to tweak, of course. But however, that may not be all of it, because there is a lot of things that must be in place for this to work. And the first thing, as we already learned a little bit about from Danny, is of course representation is crucial, that you have a good representation in your machine learning. Because surprisingly enough, if you have a good representation, if you have selected the good set of features as input, then it really doesn't matter what approach you use. They all work fairly good. But if you have the wrong representation, if you have not got the right features there, no method will help you. You are lost. So, and typically this requires a lot of work to find the correct features. And then I should say, of course, that deep learning is, the reason it is very popular and very successful is that it is one way to actually help you create useful features or find useful features in a more automatic way. And many times you can do that, but it won't help you every time. So you still need to, there still will be some handcraft here to find the correct features, or at least select a method that will help you find the right features. And just to tell us a small anecdote about this thing. This is the front page of an artificial neural network book that came in 1969. On that time, the neural networks were only one layer, or essentially one layer. So they could only do what Danny referred to as linear classification or linear discrimination of classes. So there were, but still, there was a big hype in neural networks that now, we don't have to understand the problem. We can just let the network learn for us. We don't understand it ourselves, and it will solve any problem. We can solve any problem with these very simple things. So there was a big hype. And this book, it's a fantastic book. It's extremely good. It's full of insights and hints and recommendations, but because it recognizes what you cannot do. And it tells you why, and it tells you how to get around it and how to get on. But it completely killed the neural network field for 15 years. Everyone went, oh, you can't solve anything. Oh, then this is just shit. Let's leave it. So it didn't help that it gave you the pointers where to go. It pointed to multi-layers network. You need to get above this XOR problem by adding more layers and so on. But it didn't help. The network was dead. The field was completely dead at that time. And it was kind of unfair to give up the field just because there were some things that were not easy to solve by neural networks. Because with the the problems they used as example that are hard to solve, it was not only the XOR problem, it was something they call the connectivity predicate. If you have a picture with black and white pixels, and you ask yourself, if the black pixels here in the picture are connected, then this is class 1. If it's not connected, then it's class 0. And that was something you couldn't easily solve without actually considering all pixels at once in the picture. So it's a very difficult problem. But frankly, humans have a huge difficulty solving that as well. Because can you, with a quick glance, determine which of the upper or the lower red figure is connected or not? I'll give you 5 seconds. Okay, did you see which one is connected? The lower one is connected, the upper is not connected. So we can't do it either at a glance. We have to do it sequentially, follow the lines and so on. That's quite something different than what a neural network does. So it's a little bit unfair to give up the field just because there are things that are not easy to solve with neural networks. However, the neural network field resurfaced 15 years later with this multi-layer perceptrons, and then it started flourish again. But anyway. So that was about the importance of representation, because the answer there is how to overcome that. You need to represent your input in the right way. It's very difficult otherwise to solve it for any method. And the second thing that must be in place is, of course, data cleaning, because data is not clean. In typical real-world data, there are missing data, there are out of sync fields. Somehow we have seen so many databases where suddenly something has come into the wrong column. We don't know why this happens, but it does. Misspellings if it's text data, special values. Surely the temperature can't be minus 9,999. So we can use that value to mean something else in our database. And then you use linear regression on this, and you will go completely wrong, for example. Various noisy things. So, sources with different meanings. So, we reused this column when we rebuilt our system. So now it means something different. But inconsistencies, and of course a lot of irrelevant data that is not at all useful. So these must all be handled before you can start doing something really useful with your machine learning. I will just move on. The next important thing is, of course, validation. So that's why we have if you only look at the performance you have when you test your method on your training set, the same set you use to train your method, you will always think you have a much better performance than if you actually use another test set or verification set. Because the method you have has always a tendency to overlearn the things you show it. So it will focus on small details that are not relevant, but makes the system recognize this very image and remember somehow what class it is. So which is quite useless for when you want to do generalization, because that is what you want to do. You want to show a completely different picture and still get out something useful. And so there are these methods of using validation sets, but then I just want to warn you that there are thousands ways that you can fool yourself and still think you have better performance than you actually will in the real life. For example, even if you use a validation set and then you start tweaking the parameters of your method. Okay, I got this performance on the validation set, and then you tweak your parameters a little bit. It goes worse. You tweak it. Now it got better. Then suddenly you have information about the validation set has seeped into the training anyway, because you tweaked your parameters so much. So you have now found the parameter settings, not the generally best parameter settings, but specifically the parameter settings that give the best result on that specific validation set. Nothing else. So when you get new data again, you will get much worse performance. And consider this. Suppose you have a benchmark on the web somewhere. Everyone uses that benchmark and uses it to publish their data, or their methods and the performance of the methods. So everyone uses that very benchmark, and they tweak their methods, and they compete, and somehow the research community suddenly finds the best methods are weeded out. Yeah, the methods that perform the very best on that specific benchmark, not in general. So, as I said, this is a tricky thing. Whatever you do, you will always think you have something that performs better than it actually will in the real world, just so you know about it. Yeah, some way to guarantee overtraining, too complicated model, too few samples, and so on, and evaluate several models with the same validation set, that is tweaking your parameters until it works. Finally, deployment. You can, when you use your method in the lab, everything is in a controlled environment. You know your training set and your test set, and when you try to use this in the real world, it's on its own. The real world is always more mean to you. For example, is the world really constant? Is the distribution of your data in the real world really the same as you had in your training set once? Is it static, or will it change over time? Do you have to retrain your network? What guarantees do you then have that you will have the same performance, and so on? So, and maybe most important, there is a distinction here between, for example, prediction and control, or prediction and causation, or correlation and causation, that will easily come and bite you if you're not careful. So I will give you some examples actually of, related to this, what you should not do in machine learning. So this is, the first example is actually from the paper and pulp industry. There is something called a kappa number, which has to do with the quality of the paper. So you know that you want some quality. You're trying to achieve a specific value of this kappa number. I have no idea what it really means, but so it is. And then everyone knows that this is negatively correlated to the alkalinity of your pulp. So you can control the kappa number by actually adjusting how much alkaline thing you threw in there. So, however, when they started to measure this in the pulp, so they actually, someone working at this with this measured the kappa number and the amount of alkaline that they had in there, and noted that the correlation was positive. How come? So this is what a machine learning would notice, a positive correlation between alkalinity and the kappa number if they actually put in the sensors there and try to learn this, if you wanted to learn how to control this thing. So how come? Everyone knows that it should be a negative correlation. But however, this is of course due to the control system. So the control system is trying to achieve a certain kappa number. So when the kappa number is too high, it throws in more alkaline to get it down again. And when it's too low, it does not throw in any more kappa to get it up. So what you see is not the real correlation you want to see. You see the effect of your control system. So if you have an effect of a control system, it erases or even reverses, as in this case, the real correlation. But it's the real correlation you will see when you try to learn this. So another example, in an attempt to make autonomous cars, this was 20 years ago or more, before these autonomous cars that are running now. So this was a very early attempt. You had a camera, you were looking for the white lines, and you had a neural network. You want to train the neural network to see that if the white lines are too much on one side, you should put the steering wheel that way, and if it's on the other side, put it on the, turn it on the other way around. And they trained this with a very skilled driver to make sure that you got a very high quality training data, staying in the middle of the road, as they wanted to do. And actually, it really worked. The neural network could, to a large extent, stay in the middle of the road quite much, recognizing these white lines. However, it worked as long as the car stayed in the middle of the road. But at once it got a little bit outside, where the driver, the expert driver, had never been, the neural network had no idea what to do. And you can only imagine what happened. So training with a too good control system gives you no training data what happens outside your optimal domain. And that is, you need to know what happens there, because that's how you can stick in the optimal domain, because you must know how to get back there from outside. So third example, landing a JAS plane. This was in the 90s, also a long time ago. And there was a master's thesis work that was about trying to land a JAS plane automatically, because there had been these 2 crashes, and they thought that maybe without the pilot everything will be much more safe. So they recorded the position of the plane and the altitude and the angles and where the landing pad is and so on. And also they recorded this steering pin, the position of it, or the pressure on it. So, and to have really good data here, they sampled it every single millisecond to make sure that it didn't miss any important thing here. And yeah, the network worked amazingly. It managed to predict the position of the steering pin the next millisecond, because that's the thing you want to find out. How should I put the steering pin now to land the plane safely? So in every millisecond you try to predict, how should I put it now, given all the previous time steps, the position of the plane and the stick's position the previous milliseconds. And it worked excellently, over 99.9% accuracy. So perfect, it's just to put this in the plane and let it land then. Unfortunately, the neural network was smarter than as so often, smarter than the designers, because the network had found out that it could ignore all the values except the position of the steering pin the previous millisecond, because it's very, very likely that the position this millisecond is almost the same as the previous millisecond. So the network didn't need to move the steering pin at all, which in one sense, just for the case of the JAS plane, could have helped, because the crashes were because the pilot moved the pin too much and didn't get any feedback. So just releasing it could have helped. But in general, even if you think you have a perfect prediction, it can be completely useless for control. So that's all. In this machine learning context, actually selecting the method, that's the least problem. There are huge tasks around it, where data cleaning and deployment are probably the biggest tasks. So in general, if you want to use machine learning, this is what you think about. You need to understand your problem and where the data comes from. You need to have at least to select a good representation, or at least have a method that helps you select this representation. It's not for free. It's not completely for free. You need to think, what features do we really represent? Take care with validation. It will bite you. And correlation is not causation, as in these last examples. Watch out for it. And then keep it as simple as possible. The more you complicate it, the more it will overtrain, and the more it will fool you. It will find some other way to do it. Still, it needs to be as powerful as you need to solve the problem, of course. But yeah, that's it.
Right. Thank you, Anders. So, before we break for coffee, I think we can have time for one question. Do you have one question for Anders before we break? No, I'm just going to ask a very quick question. So actually, you talked about the rise of neural networks in the 60s, and then they went out of fashion due to Minsky and Papert, and then they rose to prominence again in the 80s and so on, and then they disappeared because of various
statistical
reasons.
methods.
Yeah. And now we have a resurgence in deep neural networks and so on.
Yeah.
Do you think we run the risk of this happening again?
That requires a balanced answer. Otherwise, Danny will hit me. And he's so clear. But I think that deep learning is one of the most, like many others think, one of the most exciting things. Clearly, we're onto something. We need to have these higher order representations to build up a higher stack of things. I think that is part of the solution. But clearly, yeah, we can see the hype again. Everyone jumping on this bandwagon without really knowing what they are doing. There will be a crash. I think it's a very valuable method. This is a solution. But unfortunately, as you saw with this first neural network crash, people are so volatile. If it doesn't fulfill the promises, they leave the field, unfortunately.
All right. Okay. Thank you.